Welcome to the Deep Dive, the show where we take on some of the densest, most technical topics out there and strip them down to their core, often surprising brilliance. And today we are diving deep into the material that, well, literally forms the bedrock of our modern civilization, Portland cement.
It really is astonishing when you think about it. This is the most widely used man-made material on Earth.
Is that right?
Oh, yeah. We use twice as much cement every year as we use steel, aluminum, and plastic combined. And yet, for something so essential, most people, even a lot of people building with it, just treat it as a simple, inert, gray powder.
And we know it's anything but simple. So our mission today is to cut right through that assumption. We're providing you, the learner, with what we think is the essential shortcut to technical fluency in cement chemistry. We're moving past that simplistic idea of concrete and getting into the really specific high-temperature chemical reactions, the crystal structures, and all the microscale dynamics that dictate whether a road lasts 5 years or 50.
And I think we have to start by accepting a foundational truth here. Cement is not stable. It is a finely tuned, kinetically controlled system, and it's made up of what we call metastable mineral phases.
Okay, so metastable meaning not quite stable, but not actively falling apart.
Exactly. And every single aspect of its eventual performance, its strength, its speed of set, its resistance to chemical attack, all of it is entirely dependent on these tiny, minute compositional adjustments. And crucially, the precise thermal history it experienced inside the kiln.
So the heating and cooling.
The heating and cooling. If you alter the firing process or the cooling rate by even a small margin, you fundamentally change the crystalline structure of the key strength givers. It's that sensitive.
All right, so let's get into it. But before we can talk about the chemical behavior, we have to learn the language, right?
We do.
Cement chemistry relies on this shorthand that, at first glance, it just looks like alphabet soup. But it's actually an incredibly efficient way to represent these complex oxide combinations.
That's exactly right. We use single letters to represent the major oxides that make up, something like 95% of the cement mass.
Okay, so let's run through the big ones. C is for.
C is calcium oxide, CaO. That's the dominant component.
Got it.
S is silicon dioxide, SiO2.
A.
A is aluminum oxide, Al2O3.
Okay. And F?
F is iron oxide, Fe2O3. And then the last of the big five is M, which is magnesium oxide, MgO.
So CSAFM. When we talk about the primary strength component then, which is C3S, we're really just translating that as tricalcium silicate.
Precisely. C3S is just the shorthand for 3CaO SiO2. But here's a really critical insight, and you have to get this right from the start. Using this notation is purely a convenience. It's a historical artifact that just defines the ratio of oxides.
Okay.
It does not mean the constituent oxides exist separately within the actual crystal structure of the resulting mineral.
Right. So tricalcium silicate is its own single thing.
It's a single, complex, highly ordered crystal. It's not three little molecules of lime glued to one molecule of silica. And that distinction really matters because the unified crystal structure is what allows for substitution, which is, the key to cement quality.
And we'll see other letters pop up now and then, right? Like H for water or K for potassium oxide.
Yes, H for H2O, K for K2O, and you'll see S bar for sulfur trioxide, SO3. But C, S, A, F, and M. They're the core five that really build the house.
The ratio of those five determines everything.
Everything. From how easily the raw meal clinkers in the first place to the eventual durability of the concrete decades later.
So let's talk about the standard material that most people are familiar with.
Yeah.
Ordinary Portland cement, or OPC. This is the gray powder that defines modern construction. It's the general purpose workhorse.
And it's standardized globally. You might see it as European class 42.5 MPa, which guarantees a minimum strength, or maybe as ASTM types I and II in North America. These standards aren't just, arbitrary guidelines. They impose strict compositional limits, and I think understanding why those limits exist is probably the quickest path to understanding durability engineering.
The limits are there because if you exceed certain percentages, you are literally building a delayed structural failure into the cement from day one.
That's it.
What's the biggest culprit on that trouble list?
Well, there are two phases that react far too slowly, and they're the big ones to watch. Magnesium oxide, MgO, and free lime, which is unreacted CaO.
Oh, wait.
The content of MgO is usually restricted to a 4 to 5% maximum. The real danger starts when MgO exceeds about 2% of the clinker mass. Above that threshold, it starts forming a phase called periclase.
And periclase sounds innocuous enough, but it's an engineering time bomb, isn't it?
It is the definition of a time bomb. Periclase isn't very soluble, so it reacts extremely slowly with water. We're talking over months or even years. But when it finally does react, the hydration product it forms requires a much, much larger volume than the periclase it replaced.
So it expands.
It causes a massive, destructive internal expansion within the hardened concrete long after construction is finished. And free lime behaves similarly, though its reaction is usually a bit faster, appearing in the first few weeks. That limit exists purely to ensure long-term volume stability.
So the standards are basically guarding against a deferred detonation. What about the sulfates? I see a limit on those too.
Sulfur trioxide, or SO3, is also very strictly controlled, typically staying within 3 to 5% for OPC. And just like MgO, excessive SO3 causes destructive expansion, often through the formation of these expansive sulfate attack phases, like secondary ettringite later in the concrete's life.
And then there are the alkalis, sodium and potassium, which are notorious for attacking certain types of stone, right?
Yes, the alkali content Na2O and K2O is often restricted to something like 0.6% equivalent Na2O. This control is aimed squarely at mitigating something called alkali-silica reaction, or ASR. It's a major durability hazard where the high concentration of hydroxide ions, which are fueled by these alkalis, reacts with specific reactive forms of silica in the aggregate, in the stone. And this reaction forms a hydrogel that swells, literally cracking the concrete from the inside out. All these limits are direct risk mitigation against known long-term chemical failure modes.
To really illustrate just how sensitive this chemistry is, let's look at a specialty product. White Portland cement. This material is visually and economically very distinct, but chemically, what makes it so different from the standard gray OPC?
Well, it's chemically engineered to be pretty much the extreme opposite of a sulfate-resisting cement. The normal dark gray color of cement comes predominantly from the iron oxide in the ferrite phase, the Fe2O3.
Right, the F.
The F. To achieve whiteness, you have to virtually eliminate that color source, which means minimizing iron, manganese, and titanium in your raw materials.
Which has got to be incredibly difficult and expensive because those minerals are just everywhere in most earth deposits.
Oh, absolutely. It's nearly impossible to source raw materials that are entirely free of iron oxide. So the production method has to be adjusted. The manufacturer increases the ratio of alumina Al2O3 to iron oxide in the raw meal. But the real secret is in the firing and cooling.
Okay, what do they do?
They have to produce the clinker under slightly reducing conditions, so less available oxygen, and then, this is critical, employ extremely rapid quenching the moment it exits the kiln.
And does that reducing condition somehow change the valent state of the iron, making it less of a colorant?
That's exactly it. If the iron is forced into the Fe2 plus state, the ferrous state, instead of the normal Fe3 plus ferric state, its coloring power is greatly reduced. And that rapid quenching is the final critical step. It doesn't give the remaining color-forming phases a chance to fully crystallize or aggregate. It just locks the chemistry in a non-equilibrium state.
So in white cement, the manufacturer is basically embracing that kinetic compromise we talked about, forcing the chemistry to stop before it can reach its thermodynamically preferred darker state. That is a beautiful illustration of high-stakes chemical control.
And that rapid quench, which is often achieved by just spraying water onto the hot clinker, also results in the formation of a higher proportion of amorphous glass compared to a regular OPC. This glassy matrix helps trap any trace colorants away from the crystal structures. It's a high-cost, high-precision product that just shows how complex the basic material can be.
All right, let's move on now to the actual power generators of cement strength, starting with, well, the undisputed king, alite, or tricalcium silicate, C3S. This is the phase that's responsible for most of the early and overall strength development.
C3S is absolutely the most important hydraulic phase, but it's deeply complex. You can't just describe it as a single compound. It actually exists in multiple crystalline forms, or what you call polymorphs.
Polymorph.
Yeah, rhombohedral, monoclinic, and triclinic. These forms are geometrically related, but they vary in their internal symmetry and structure. And the exact polymorph you get influences its reactivity with water.
And this complexity comes from the fact that pure C3S is highly unstable at room temperature. It requires what we used to call impurities to even exist, but they're not really impurities at all. They're essential stabilizers.
That is a great way of putting it. Those impurities are essential elements like MgO, Al2O3, and F2O3 that substitute into the C3S lattice during clinkering.
So they slot right into the crystal structure.
They do. They change the crystal geometry just enough to make the structure stable at lower temperatures, locking in that reactive phase. For example, the amount of MgO that can dissolve into C3S depends heavily on temperature. You can get about 2% in at 1550 degrees Celsius, and that drops a bit at lower burning temperatures.
So when we analyze a finished clinker, the maximum amount of magnesium that didn't form that problematic periclase is often contained right here, inside the structure of the key strength giver.
It's a really elegant way for the system to manage these otherwise dangerous elements. And the aluminum and iron ions, they compete for these substitution sites, and their presence is what shifts the C3S structure from one polymorph to the next, for instance, stabilizing the monoclinic forms, which are slightly more reactive than the triclinic forms, though, all of them are highly reactive compared to belite.
That structural sensitivity is just incredible. And to illustrate this point, the natural world has actually mirrored this highly engineered process.
Yeah, this is fascinating. There's a naturally occurring substituted C3S mineral called HFW. It's found in rocks that were formed under conditions remarkably similar to those inside a high-temperature cement, kiln low oxygen, high-heat environments created by, say, combustion processes in nature.
Wow.
HFW proves that the crystal substitution we rely on for C3S stability is a completely natural chemical phenomenon, even if we usually create it artificially on a massive industrial scale.
Okay, next up we have belite C2S. This one is often seen as alite's slower, more patient sibling. It provides excellent long-term strength and chemical resistance, but its value is entirely dependent on its crystalline form.
Belite, or decalcium silicate, is structurally even more complex than alite. It boasts 5 distinct polymorphs: alpha, alpha prime H and L, beta, and gamma. And these differences are rooted in really subtle changes in the orientation of the silicate tetrahedra within the crystal structure.
And this leads directly to the core problem, what's called the reactivity paradox. Why is it so crucial that we prevent the formation of that gamma form?
The distinction is absolutely vital. The beta C2S polymorph is hydraulic. It reacts slowly with water, provides strength after 28 days, and it contributes excellent late-age performance and resistance. The final, low-temperature gamma C2S polymorph, however, is virtually inert.
So it does nothing.
It has no cementing ability whatsoever. Worse than that, it undergoes a volume increase upon transformation from beta to gamma, about 10 to 12%, which leads to a complete dusting of the clinker, rendering it completely useless.
So if the kiln operator allows the cooling process to stall in that critical temperature range, they're literally producing dust instead of cement clinker. That's a massive economic failure baked right into the process.
It is a critical kinetic failure. And just like alite, belite is stabilized by substituting these foreign elements. Belite is often a sink for things like K2O, N2O, TiO2, P2O5, and Mn2O3. And these substitutions are what stabilize the desired hydraulic beta form, preventing that transition to the inert gamma form during cooling. So elements that might be minor in the overall clinker composition play this disproportionately large role in making sure belite actually contributes to strength.
Okay, so if the silicates, the C3S and C2S, are the strength engine, the remaining phases, aluminates and ferrites, are kind of the gatekeepers of set time and the controllers of color and early heat. Let's look at tricalcium aluminate, C3A.
C3A is notoriously reactive. If you mix pure C3A with water alone, it reacts almost instantaneously in what we call a flash set.
Right.
So this phase is a liability for set control, but it is necessary for achieving high early strength, and it's just an unavoidable result of using aluminous raw materials. When it hydrates by itself, its products are weak and unstable, so its main function in OKC, which is controlled by gypsum, is purely kinetic. It controls the early stages of hydration and heat evolution.
And it also demonstrates this incredible structural plasticity, taking up large amounts of other components.
It does. C3A has a very high substitution capacity. It can incorporate significant amounts of alkalis, sometimes up to 14% of Na2O or K2O at high temperatures. These alkalis substitute for calcium and are then subsequently released during hydration, contributing to that ASR risk later on.
And now to the ferrite phase, which is visually critical because it gives OPC its signature gray color.
The ferrite phase is best described as a continuous solid solution series, Ca2, AlSFO1 by 2O5, which is commonly simplified to C4AF. What this means is that iron and aluminum can substitute for each other across the entire series, continuously changing the crystal's internal dimensions.
And its structure is?
Its crystal structure is orthorhombic.
So the color then is directly linked to the iron content, the Fe2O3.
Exactly. The gray color comes from that iron component. The density and the crystal parameters change continuously depending on that alpha ratio. And understanding this ratio is vital for specialized cements. I mean, reducing the Fe component is the whole point of making white cement. But it's a delicate balance because the aluminate and ferrite phases often require the presence of each other to form correctly in the clinker.
Okay, let's move into the manufacturing itself. Cement manufacturing is essentially a massive high-temperature chemical synthesis operation. What are the key raw ingredients going into this 14/50 degrees Celsius reactor?
The ingredients are remarkably common. Limestones, which are primarily calcite, KCO3, provide the bulk of the calcium component. Then we add siliceous and argillaceous components, which are typically clays and shales containing minerals like alite and kaolinite, and they provide the silica, alumina, and iron needed for the C2S, C3S, C3A, and C4AF.
And the single biggest operational challenge in cement production, historically anyway, was energy consumption. We often hear about the contrast between the old wet process and the modern dry process.
And the difference is absolutely monumental, and it's all about the heat budget. Theoretically, you need about 1,750 kilojoules of heat to convert 1 kilogram of raw meal into clinker.
Okay.
In the traditional wet process, the raw materials were mixed as a slurry containing 30 to 35% water just to make it easier to handle and homogenize.
But the amount of fuel required just to evaporate that water must have been catastrophic.
It was. The modern dry process is vastly more thermally efficient because it uses these preheating towers and calciners to dry and heat the materials sequentially. It avoids the tremendous amount of latent heat required to flash off that 30 or 35% water content.
Makes sense.
And even though the dry process requires a bit more electricity for grinding the raw meal, the fuel savings are so dramatic that the dry process is overwhelmingly the industry standard today.
Let's follow the material as it moves through that kiln system. It's a progression of chemical breakdown and reformation. What's happening at the very beginning?
Well, as the temperature rises, the raw materials undergo what we call calcination and thermal decomposition. So the calcite, KCO3, breaks down into CaO and CO2. The clay minerals also break down, releasing their silica and alumina.
And this leads to a temporary non-equilibrium phase that is crucial to monitor the free lime maximum.
Yes, this is a vital operational point. As the KCO3 decomposes into CaO, or free lime, its content temporarily spikes. It often reaches as high as 17% of the total clinker mass at around 1,000 degrees Celsius in the kiln.
So that's like a progress marker.
It's the key chemical indicator. This free lime is highly reactive, and it must subsequently react with the newly released silica and alumina to form the necessary silicates, C3S and C2S. The peak of that free lime is the signal that the components are fully broken down and ready for the synthesis reaction. So before the final clinkering phase occurs near 1450 degrees, you can detect several intermediate products: free lime, periclase, poorly crystalline belite, ferrite, and often a highly reactive calcium aluminate, C12A7, if there's enough alumina present. It's important to note that the less basic phases, like Ca or Ca2, are typically absent at this stage, which tells you the system is successfully driving toward the desired calcium-rich final phases.
Okay, we've hit the peak temperature now, around 1450 Celsius. The raw material is no longer just a collection of solids. It involves a liquid phase, which I understand is key to the entire process.
The formation of the liquid phase, or the melt, is absolutely essential. It acts as a tremendously effective solvent and flux. Cement clinker formation requires this liquid to facilitate rapid diffusion and reaction.
Right.
The key kinetic step in forming the strength-giving C3S is the diffusion of calcium ions through this liquid layer that coats the lime clusters. Without that liquid, the solid-state reaction would be impossibly slow.
And what are the chemical characteristics of this liquid?
It is extremely basic and highly fluxing. Data from phase equilibrium studies show that the liquid in equilibrium with the silicates at 1400 degrees is very high in CaO, often 54 to 57%, and it's also rich in Al2O3, which can range from 15 to over 30%. Its high reactivity is what allows the system to achieve its final composition so quickly.
And the dynamics of this liquid phase also dictate the size of the elite crystals, which in turn dictates the speed of strength gain.
Yes. There is a broad consensus that the optimum size for elite crystals, if you're aiming for the best 28-day strength, is around 15 micrometers. The smaller the crystal, the more surface area is exposed, and the more active it is in hydration because it contains fewer structural defects.
Okay, but how do you control that?
Well, there's a fascinating industrial debate about crystal size control. Is it controlled by how fast you heat the raw meal to clinkering temperature? Or is it controlled by the duration the material spends at high temperatures, which allows for recrystallization and growth?
So even after all these decades of manufacturing, there's still scientific disagreement on how to best achieve that ideal 15 micrometer target.
Absolutely. The goal is small crystals for maximum reactivity, but realistically, most production clinkers have average sizes that exceed 15 micrometers. It's a constant compromise between crystal kinetics and industrial throughput.
Okay, so the chemistry has been successfully forced at 1450 degrees. Now we get to the cooling stage, the quench effect, and this introduces defects that can either save the product or completely ruin it.
The cooling rate is absolutely pivotal because, as we've established, cement phases are rarely in true thermodynamic equilibrium. Non-equilibrium cooling immediately creates these microstructural features like chemical zoning in the ferrite crystals.
Zoning meaning the chemical composition is not uniform across the crystal itself.
Correct. The core of a ferrite crystal might be richer in iron, in F3 plus Wm, while the outer regions are richer in Al3 plus because they crystallized at slightly different temperatures as that liquid solidified. This is purely a function of the rapid non-equilibrium cooling.
Let's go back to MgO for a second. We need to keep it locked away. Does the quench help with that?
Fast cooling is the chemical safeguard against destructive MgO. If you cool rapidly from high temperatures, say above 1500 Celsius, you force the MgO to remain in solid solution within the aluminate and ferrite phases, where it's benign.
And if you cool slowly?
If cooling is slow, any excess MgO above that solid solution limit will crystallize out into large reactive periclus crystals, the exact phase that causes that delayed destructive expansion.
And the ultimate thermal failure scenario is if the cooling is slow enough to start decomposing the alite itself.
That is the nightmare scenario for any plant operator. If the clinker spends too long in that intermediate temperature range, specifically 1250 down to 1100 degrees Celsius, the C3S can actually start to decompose. It reverses course, breaking down into a mix of belite, C2S, and lime, CaO.
Oh, wow.
This is especially prevalent if the clinker was fired under mildly reducing conditions. You lose your primary strength phase, and you increase your dangerous free lime content at the same time.
We mentioned earlier that white cement uses quenching to encourage glass formation. How much amorphous glass is typically found in standard gray OPC?
Surprisingly little. Quantitative analysis of standard OPC clinkers shows minimal to no amorphous glass unless they were extremely fast quenched. Slow cooling, for instance, taking 6 minutes to cool from 1300 to 1100 degrees, actually favors the full crystallization of the aluminate and ferrite phases rather than forming a glass. So glass formation is truly limited to high viscosity liquids or ultra-fast quenching.
So the environment inside a modern preheater kiln is this high-stakes chemical loop involving volatile materials constantly cycling between hot and cold zones. What are these key volatiles and why do they cause so much operational grief?
The main culprits are the alkalis K2O and A2O and sulfur SO3. At high temperatures, these exist often as a vapor or as sulfate melts. They volatilize in the hot zone, and then they condense or react as the material cools below 1300 Celsius.
And this cycling creates a feedback loop that can actually choke the kiln.
Exactly. This is one of the most persistent real-world engineering problems in the industry. These recycled species form low-temperature melts, complex alkali, sulfate, and chloride systems that can start melting dramatically below 700 degrees Celsius.
So you've got liquid way too early in the process.
Way too early. Think of it. Material that is still relatively cool, well before clinkering temperature, is turning into a sticky, low-viscosity liquid. And that sticky liquid coats dust particles, causing them to adhere aggressively to cooler surfaces and narrow passages. This leads to the formation of these hard, obstructive kiln rings and deposits in the preheaters.
And chlorides make it worse.
Oh, chloride compounds significantly worsen this issue because they favor evaporation by forming volatile alkali halides, which just accelerates the transfer of these species into the cooler parts of the system. Managing this volatile cycle is a constant, expensive battle for every single cement plant.
Okay, so once we take that finished clinker, grind it with gypsum, and add water, we start what is arguably the most important chemical process in the world: hydration. What are the two main products formed when the silicates, C3S and C2S, meet water?
They form two primary hydration products: the poorly crystalline calcium silicate hydrate gel, or CSH, and crystalline calcium hydroxide, or CH. The CSH gel is really the engine of concrete. It provides the cohesive, strength-giving matrix. The CH is often seen as more of a byproduct, necessary to maintain high alkalinity, but structurally, it's quite weak.
And we need a reliable way to track how far this reaction has progressed, the degree of hydration. And this introduces the concept of non-evaporable water.
Non-evaporable water is a crucial empirical measure. It represents the mass of water that's still held by the cement paste after a very stringent drying process, like de-drying, which is equilibration at -79 degrees Celsius under a high vacuum. It's an indicator of the amount of hydrate that's been formed.
But you said it's an empirical measure, not a precise chemical measure. That seems like an important distinction.
It is. It's vital for you to understand that non-evaporable water is not the same as chemically bound water. Even at -79 degrees, the interlayer water within the CSH structure is still slowly being removed. So while it's a standard for measuring the extent of the reaction, it does slightly underestimate the total amount of water that's chemically incorporated into the crystal structures.
Okay, so the hydration of C3S is not a steady process. It's more of a roller coaster ride. It follows this classic sigmoidal curve, a fast start, a long pause, and then a rapid acceleration. That pause, the induction period, has been a mystery for decades. Why does the reaction essentially just stop before it rapidly accelerates?
The induction period can last anywhere from a few minutes in warm conditions to many hours in cold or retarded mixes. It's the period where the material remains plastic, workable. For years, there was no single consensus on why it happened. However, the evidence now strongly suggests it is a combined effect involving both physical blockage and solution chemistry.
Okay, so let's unpack those two forces. They're working together to create this pause.
Right. First, you have the physical barrier theory, the very rapid initial reaction, which happens within minutes of mixing, deposits a semi-protective, ultra-thin layer, we call it product B, on the surface of the C3S grain.
And now think of that.
It's only about 1 nanometer thick, but it's non-uniform, and it's dense enough to significantly isolate the C3S from the bulk water solution, which slows the ion exchange down dramatically.
So the cement grain essentially seals itself off, but not perfectly.
Exactly. And at the same time, the solution chemistry theory is at play. Even though the reaction is slowed down, ions, specifically calcium and hydroxide ions, continue to dissolve into the pore solution. They just build up very, very slowly during this induction period.
And then something triggers the end of the pause.
The pause terminates when these ions reach a critical threshold of supersaturation. Once that threshold is hit, it triggers the mass, almost instantaneous precipitation of CSH and CH throughout the available space, and that initiates the dramatically fast acceleratory period.
That makes perfect sense. So it's not just a barrier. It's the solution struggling to accumulate the necessary chemical density. This combined theory is a really beautiful piece of kinetic modeling.
It is. And the low rate of dissolution during the induction period can really only be explained if the concentration gradient of these ions near the grain surface is extremely high, which supports the idea that that initial product layer is really doing something to slow the release of material. It's chemical patience being rewarded with structural growth.
So once the hydration accelerates, the internal structure of the paste starts to define itself. When engineers use backscattered electron imaging, they can clearly see different zones based on density and composition. What are the key regions we need to identify in the hardened paste?
Backscattered electron imaging, or BEI, uses contrast based on atomic weight, so areas that are rich in calcium appear brighter. And we can identify 4 main zones that define the microstructure.
Okay, what's first?
First, you have the unreacted grains. These are the brightest phases, typically alite or ferrite, which just haven't fully reacted yet.
Yeah.
Second, calcium hydroxide, CH. This appears slightly darker than the unreacted phases, and it tends to be either massive and crystalline in large voids or finely dispersed throughout the paste, especially in low water-cement ratio mixes.
Okay, then the CSH itself is divided.
It is. You have the inner product, CSH, which is the dense, high-quality CSH gel layer that forms in situ, right where the original clinker grain used to be. It's highly dense because it forms in a very restricted space.
I see. And then the fourth.
And fourth is the outer product, or the matrix. This is the CSH that precipitates into the original water-filled space. It's often less dense, and it generally contains the products from the hydration of the interstitial phases as well.
So that inner product is inherently denser and higher quality because it's so tightly constrained by the shape of the original grain.
That's a key microstructural insight, and the CSH gel itself is fascinating. It's poorly crystalline, sometimes described as quasi-amorphous, but it derives its structure from a natural mineral called tobermarite. However, cement CSH has structural defects missing silicate tetrahedra and a much higher K-Si ratio, typically 1.5 to 2.0 in C3S pastes, compared to tobermarite's lower ratio.
How does that look physically? We hear descriptions like foils or fibers.
Well, when it's viewed under wet conditions, it often has a foil-like or a honeycomb morphology. But when you prepare a sample for high vacuum imaging, the delicate structure collapses due to the loss of water, and that results in the characteristic fibrous or rolled-up flake morphologies you so often see in published images.
Now, back to those reactive aluminates and ferrites. Their hydration, which is controlled by gypsum, produces the well-known AFD and AFM phases.
That's right. In the initial phase, when gypsum is abundant, the aluminates and ferrites react to form etronite, which is the AFT phase. This grows as these long, distinctive rod-like crystals. Then, as the sulfate supply from the gypsum is depleted, usually after the first few days, the etronite becomes unstable and it reacts with any remaining aluminate to form monosulfate, the AFM phase.
But I understand that this conversion from AFT to AFM isn't always guaranteed, especially in real-world scenarios.
That's a great point. Even a small amount of atmospheric carbon dioxide, which dissolves in the pore solution, can stabilize the etronite, preventing its conversion to monosulfate. And this means that in many field concretes, etronite can persist indefinitely, which is critical for understanding later durability issues like delayed etronite formation.
Okay, so all these microstructural components, the CH, the CSH, the unreacted grains, they form this massive composite material that is inherently porous. And this porosity is the single greatest determinant of long-term durability. How do we categorize it?
We use the foundational Powers Brownyard model. It defines the total porosity as the sum of two types: gel porosity, which are the extremely fine micropores within the CSH itself, and capillary porosity, which are the larger spaces that were initially occupied by the mixing water that weren't filled by hydration products.
And the aha moment for anyone who wants to understand durability comes when they realize that the connectivity of those pores is actually more important than the volume of the pores.
Absolutely. This is the concept of percolation theory. Percolation describes whether a continuous, uninterrupted path exists through a porous material. If the capillary pores remain connected, water, oxygen, chlorides, and sulfates can easily transport through the concrete, drastically lowering its resistance to chemical attack and corrosion.
So durability engineering is essentially a race to disconnect those capillary pores.
That's it exactly. You want the system to reach a critical threshold where those larger connected capillaries are broken up, forcing any penetrating agent to travel through the much slower, more tortuous gel pores.
Right. And do we know where that threshold is?
Yeah, we do. Modeling calculations show us these critical thresholds. For a standard C3S paste with a common water-cement ratio of 0.5, capillary pore connectivity essentially ceases when the total capillary porosity drops below about 18%. This critical disconnection happens at approximately 86% hydration. Once you cross that 18% threshold, the permeability drops by orders of magnitude because transport is now restricted to the fine, restrictive gel pores. And that shift is the fundamental difference between high-quality, durable concrete and fast-decaying, permeable concrete.
Okay, we've established that the highly reactive C3A needs gypsum to prevent instant stiffening. But if you don't control the grinding process perfectly, you can run into two distinct setting problems: flash set and false set. They sound similar, but they are fundamentally different chemical failures.
They are completely distinct. Flash set is a true chemical problem. You get rapid stiffening accompanied by high heat evolution. It means you used inadequate gypsum, which allows the uncontrolled hydration of C3A and C4AF, and that leads to the immediate formation of this meshwork of large AFM crystals. This rapid, uncontrolled crystal growth destroys the workability and results in poor final strength because the internal structure is damaged right at the beginning.
Okay, so that's the bad one. What's false set?
False set is more of a physical or a mechanical problem. You get rapid stiffening, but crucially, there is no abnormal heat evolution, and the plasticity is regained simply by continuing to mix the material.
So you can just mix through it.
You can mix right through it. The most common cause is during the cement grinding process. The heat of grinding partially dehydrates the gypsum, forming hemihydrate. This hemihydrate then converts back into gypsum when it meets water, creating these fine secondary gypsum crystals that interlock and cause the rapid stiffening. But since no real chemical damage has occurred, remixing just breaks the crystal linkages and the concrete is fine.
Now, to intentionally delay that critical set time, we use organic retarders. How do simple compounds like sucrose or lignosulfonates work so effectively at such tiny concentrations?
They work by being highly targeted poisons. Organic retarders are typically compounds that feature oxygen atoms on adjacent carbon atoms. It's a very specific molecular structure. At very low dosages, these molecules adsorb onto the surfaces of the newly forming hydration products, especially the crystalline calcium hydroxide and the CSH.
And what does that do?
By forming a complex or a thin film, they effectively poison the nucleation sites. They physically interfere with the ability of the crystals to grow and link up, and that's what extends the induction and the setting period.
Okay, let's talk about superplasticizers, or high-range water reducers. These are perhaps the most revolutionary admixture of the last 50 years. They allow engineers to achieve incredible reductions in the water-to-cement ratio, which immediately translates into strength and durability. How do they perform this magic of liquefying cement paste?
Their function is pure colloidal chemistry. They disperse the cement grains. Superplasticizers, like polycarboxylate ethers or sulfonated compounds, allow for water reduction up to 30% while maintaining workability. Or they allow you to create true flowing concrete. And this is all accomplished through powerful electrostatic repulsion.
And the measure of that repulsion is the zeta potential, right?
Exactly. When these polymers are introduced, their anionic groups adsorb onto the surfaces of the cement grains. This adsorption causes the grains to develop a massive negative surface charge, and we measure this as a strong negative zeta potential, often hitting -30 to -40 millivolts.
Wow.
This high negative charge maximizes the repulsive electrostatic forces between the particles, which easily overcomes the natural van der Waals attractive forces that cause cement particles to flocculate or clump together.
That's a powerful visual. You're basically changing the electromagnetic environment around every single grain of cement, forcing them apart from each other.
And by forcing that dispersion, the paste flows easily with significantly less water. This reduces the yield stress of the mix, allows for denser particle packing, and critically, it reduces the initial capillary porosity, which leads directly to the ultra-high compressive strengths we see in high-performance concretes. It's a direct link between nanoscale electrochemistry and macroscale structural performance.
Now, to achieve superior performance and also greater sustainability, the modern industry relies heavily on composite cements, replacing a portion of Portland cement with other materials. Let's start with ground granulated blast furnace slag, GGBs.
Slag is what we call a latent hydraulic material. It is a glassy, non-crystalline byproduct of iron production. It requires activation, which is provided by the hydroxide ions released from the initial hydration of the Portland cement component.
And it's chemically advantageous.
It is, because it reacts with the calcium hydroxide produced by the OPC hydration, lowering the overall CH content and generating additional CSH, which is known as a pozzolanic reaction.
And how does it handle that problematic magnesium oxide?
The magnesium in the slag is inherently benign. It doesn't form the expansive periclase. Instead, it forms a phase called hydrotalcite, which is a stable, non-expansive layered double hydroxide. This contributes to better sulfate and chloride resistance compared to just a pure OPC.
Okay, next up, pulverized fuel ash or fly ash, via.
Fly ash is a byproduct of coal combustion, and it's typically composed of these spherical, glassy particles. Class F fly ash, which is low in calcium, acts as a traditional pozzolan, reacting slowly with CH over time. Its fine spherical shape is beneficial in two ways. It improves workability, and the particles act as powerful nucleation sites.
What does that mean?
It means they actually accelerate the reaction of alite in the middle stages of hydration by providing these ready-made surfaces for CSH to precipitate onto.
And its alkali chemistry is key for mitigating ASR, right?
Crucially, yes. The alkali cations that are released from fly ash are less effective at raising the pore solution pH compared to the alkalis released directly from cement. And since ASR is so dependent on high hydroxide concentration, PIA substitution is a primary strategy for mitigating ASR risk.
And finally, the ultimate high-performance additive, silica fume.
Silica fume is a highly refined industrial byproduct. It consists of incredibly small, non-crystalline glass spheres, often only 100 nanometers in diameter. Its ultra-fineness provides two massive benefits. First, it has extremely strong pozzolanic activity, so it rapidly consumes CH to form high-quality CSH.
And the second.
Second, its tiny size allows for perfect particle packing, leading to a profound densification of the interfacial transition zone, the ITZ, which is the normally weak region between the cement paste and the aggregate surfaces. By tightening up this ITZ, silica fume enables the creation of concretes with phenomenal compressive strengths, sometimes exceeding 270 MPa.
Before we move to durability, let's look briefly at two niche products. First, calcium aluminate cements, or SCACs, which are used in high heat and chemical resistance applications.
CCACs are a totally different animal. Their hydraulic activity comes primarily from monocalcium aluminate, Ca. They set very fast and are highly resistant to sulfate attack in dilute acids, provided the pH stays above about 4. They're often used in refractory concrete or in sewers.
But they have that famous conversion issue that led to some high-profile structural failures decades ago.
Yes, the strength loss associated with conversion is the main drawback. At high temperatures and high humidities, the initially formed hydrate, CaH10, converts into denser, more stable phases, C3AH6 and AH3. And this phase conversion increases the total porosity of the concrete and reduces compressive strength.
So why are they still used?
Because of the chemical protection. Despite the internal strength reduction, the conversion often forms an extremely hard, non-porous surface zone that restricts the penetration of external agents. So this paradoxically provides excellent long-term chemical durability, even if the internal bulk strength drops somewhat.
Okay. And finally, expansive cements, designed to counteract the volume loss associated with drying.
Expansive cements, like Type K, are engineered to dramatically increase ettrinite formation. They rely on a phase called C4A3S bar as a key ingredient, mixed with high amounts of gypsum or anhydrate. The goal is to induce a controlled internal expansion, either through the physical forces exerted by the growing ettrinite crystals or the swelling pressure of colloidal ettrinite attracting water. This internal expansion compensates for the drying shrinkage that occurs later, minimizing cracking and often leading to self-stressing properties.
All right, let's get to the long game. Concrete durability issues. Durability is ultimately a race to maintain the protective environment for the internal steel reinforcement. The steel is safe as long as the pH of the pore solution stays high.
That passive oxide film on the steel is stable at a pH of 12.5 or higher. The two great enemies of this passivity are carbonation and chloride ingress. If either one breaks down that protective layer, corrosion starts, and that expansion from the rust leads to spalling and complete failure of the structure.
Let's detail the chemical cascade of carbonation. It's not just CO2 hitting the surface, is it?
No. Atmospheric carbon dioxide dissolves in the pore solution and forms carbonate ions. This CO2 is acidic, and it chemically attacks the cement hydrates. It consumes the crystalline calcium hydroxide, which is the primary source of alkalinity, and at the same time, it starts decalcifying the CSH gel itself, lowering its Ca-C ratio.
And the pH falls dramatically.
Yes, as decalcification proceeds, the CSH is ultimately reduced to a less protective hydrous silica structure. The pH of the concrete cover drops below 8.5, which is the critical threshold. Once that happens, the steel's passivation layer breaks down, allowing corrosion to begin rapidly in the presence of oxygen and moisture.
And chloride attack, often from road salts or marine environments, provides a totally different pathway to corrosion.
Yes. Chloride ions migrate inward through the porous structure. While some chloride is chemically bound up in the hydrates, a significant fraction remains free in the pore solution. And these free chlorides can destabilize the steel passivation layer, leading to highly localized, aggressive pitting corrosion even if the pH remains high. The problem for you to understand is that even though chloride diffusion is incredibly slow in dense concrete, once it hits the steel, the localized damage is just catastrophic.
ASR is often called concrete cancer because it's a self-propagating durability failure. It's a chemical conflict between the cement and the aggregate.
It's a reaction of massive volumetric change. It involves reactive silica phases, amorphous silica, opal, things like that, in the aggregate reacting with the high alkali concentrations, particularly the hydroxide ions, present in the cement pore solution. This chemical process generates a hygroscopic, swelling alkali silicate gel.
And this gel expands with tremendous force.
It absorbs water, it swells, and it generates immense internal pressure, far exceeding the tensile strength of the concrete. This pressure manifests as a characteristic map cracking pattern on the surface and significant internal damage, reducing strength and providing pathways for further chemical attack.
Now, this reaction has a bizarre concentration dependency called the Pessimum effect. Why does the worst damage happen at an intermediate concentration of reactive aggregate and not the highest?
The pessimum effect is very counterintuitive, and it's a cornerstone of ASR research. If you have a low amount of reactive silica, the gel forms slowly and it's dispersed. If you have a massive amount of reactive silica, the reaction happens so quickly and consumes the available alkali so fast that the resulting gel is altered.
How so?
In these high concentration cases, the abundant calcium ions are often available to convert the highly expansive alkali silicate gel into non-expansive CSH, which effectively mitigates the worst of the damage.
So a small amount of reactive material is worse than a large amount, because the small amount creates a gel with the perfect composition and distribution to swell uncontrollably. That is a powerful lesson in nonlinear chemistry.
It is.
All right, let's talk about sulfate attack. Concrete in sulfate-rich environments faces different types of attack, depending on the cation paired with the sulfate anion. When concrete is exposed to sodium sulfate, Na2SO4, what happens?
Sodium sulfate attack is primarily expansive. The sulfate ions react with the calcium aluminate hydrates and the calcium hydroxide to form two secondary voluminous phases, secondary gypsum and additional etranite. The crystallization pressure exerted by the growth of these secondary expansive crystals is what causes cracking, scaling, and eventual failure of the cement paste structure.
But the truly destructive attack comes from magnesium sulfate, MgSO4. Why is it so much worse?
Magnesium sulfate is so destructive because it directly attacks the CSH, the core strength giver. The reaction sequence is dramatically different. In the presence of MgSO4, you form gypsum and the mineral brucite, which is magnesium hydroxide. Brucite has a very low solubility. Its formation consumes hydroxide ions, and it drastically lowers the pH of the pore solution much, much faster than sodium sulfate attack does.
And that pH drop is the trigger for everything else.
Yes. The lowered pH triggers an aggressive decalcification of the CSH gel. The CSH loses its calcium, and magnesium integrates into the structure, forming a magnesium silicate hydrate, which is structurally similar to poorly crystalline serpentine. This material has no cementing properties whatsoever.
Wow.
This entire process leads to physical softening, a complete loss of cohesion, and the ultimate destruction of the concrete structure, often leaving behind only a friable silica gel.
We mentioned DE earlier, delayed etranite formation, which is the reformation of etranite that causes expansion in concrete cured at high temperatures. While DE used to be treated as a standalone failure mode, recent research suggests there's a strong synergistic link with ASR.
This connection is a critical and still evolving insight in durability science. High-temperature curing suppresses initial etranite formation. The sulfate ions are just kept in solution, but field and lab studies are now demonstrating that DF is frequently promoted or even made possible by pre-existing alkali-silica reaction.
So ASR sets the stage for DF damage. How does that synergy work physically?
ASR expansion generates microcracks and internal stress fields. Essentially, the ASR damage precedes the symptomatic formation of the secondary etranite. The expansive gel from ASR provides the localized internal space and the chemical pathways that are required for the delayed etranite to crystallize later, often forming visible veins in those pre-existing ASR cracks and at the aggregate paste interfaces.
So it sounds like ASR creates the weakness, and then DF is the follow-up attack that finishes the structure off. It's a two-stage failure mechanism where the first chemical flaw primes the system for the second, physical failure.
That's an excellent way to put it. It highlights that in durability, isolating one failure mode is often impossible. The chemical failure modes often conspire to accelerate collapse.
And that brings us to the end of our deep dive into Portland cement chemistry. We began by demystifying the essential shorthand, the difference between C3S and C2S. We moved through the manufacturing process, recognizing that the difference between a high-quality cement and a failed batch is often measured in the composition of a low-temperature sulfate melt, or just a few minutes of accelerated cooling.
We've traveled from the heat of the kiln, where MgO must be locked away by rapid quenching, all the way to the microscale dynamics of hydration, where CSH forms a semi-crystalline foil derived from tobramite. And we discovered that the entire life of concrete hangs on crossing that critical percolation threshold, that 18% capillary porosity level, to cut off the pathways for decay.
And we learned that cement is not a static material. It is a living, meticulously engineered system defined by kinetic and thermodynamic compromises. Whether it's using superplasticizers to manipulate the zeta potential of individual grains, or ensuring that supplementary materials like slag form stable hydrotalcite instead of destructive periclase, every single detail is a calculated risk.
I think the ultimate lesson is that structural survival is dictated by the subtle role of substitution and particle size. The difference between survival and catastrophic failure often rests on parts per million of an alkali, or the difference between a high-quality inner product and a porous outer product.
And this naturally leads us to our final provocative thought for you to consider. We learned that modern engineers achieve ultra-high-strength concretes by using materials like silica fume to optimize density and microstructure. Yet we know that two key failure modes, ASR and DEF, work synergistically, where internal cracking promotes subsequent chemical attack. So when we push these super-dense mixes to their extreme structural limits, optimizing for strength over resilience, what new, inadvertent microstructural failure modes might we be creating? And is there an unseen compromise point between maximum strength and maximum chemical resilience?
Food for thought indeed, as the quest for ever stronger concrete continues.
Thank you for joining us on this deep dive.